we are going to talk about 6.4 today, which is graphs of logarithms. And this section is a little tricky. All right, I would not say this is an easy section. Okay, and now I know you guys think I'm a liar, so maybe you think that this is actually an easy section, in which case that's great. All right, but it's a little tricky. So before we even get into the section, I want to review what logarithms are. There's a lot of people in this town with really loud cars. So remember what we said logarithms, right? The definition of a logarithm. Right? For example, we said something like, what is log base 2 of 8? We said there's an exponential form of this. The definition of a logarithm. This is the same as saying 2 to the y equals 8. So this logarithm is just going to be 3. Because 2 cubed is 8. Okay, that's what we said. That's what we said logarithms mean. Okay, the base of the logarithm, the bottom of the logarithm, is the same as the base or the bottom of the exponential function. Okay, so we're going to be using this fact to do graphs and get information and be able to take this section down. Okay, so example 1. Given the graph of y equals 2 to the x, graph y equals log base 2 of x. So what we have right here is the problem is going to give you a graph, then ask you to do another graph. Okay? And the key is that this problem should be easy if you know everything. If you don't know everything, this problem will not be easy. But anyway, this is the problem, what it gives you. So it gives you this exponential function 2 to the x. And it's asking you to graph its inverse function. Remember, right, that log base 2 of x is the inverse function of the exponential function 2 to the x. Exponentials and logarithms are inverses of each other. It's one of the most important things to remember of this chapter. Exponentials and logarithms are inverses. So all you have to do is graph the inverse function of this. And right, remember inverses, the whole idea of inverses is that it switches x's and y's, right? That's how we found inverse functions. We just switch the x's and the y's and we solve for y. Well, if we want to graph an inverse, we just switch the x and the y coordinates, right? So for 2 to the x, right, that has the point 0, 1. On its inverse, it's going to have the point 1, 0, switching the x's and the y's. The function has the point 1, 2. Its inverse will have the flipped 2, 1. Right? 0, 1 becomes 1, 0. For the inverse function. Oh no. Oh no. We've gotten to that point where the mechanical pencil's running out of lead and it doesn't stay up. And I hate mechanical pencils. I love pens. Oh no. So we just essentially do this with all of the points that we have, and we just graph them all. Okay? So again, we said the point 1, 2 became the point 2, 1 for its inverse. We have a point up here. This is 2, 4. 2, 4 is going to become 4, 2 on the inverse. Like so. And that's how you can graph these. You can graph every single logarithmic equation this way, by just starting with the function and then graphing the inverse. Let's do one more point. Let's do a point over here. This is negative 1, 1/2. We switch the x's and the y's here, and this becomes 1/2, negative 1. Like so. So those are some points. But also, right, what is the asymptote of this exponential function? The asymptote is a horizontal line y equals 0. So what does the asymptote look like for its inverse function? If all we're doing in this example is switching x's and y's, what is our asymptote going to be for our logarithm? Someone make a guess. What's the equation of the asymptote for the logarithm, given what we've been doing? 0, 1 became 1, 0. We just switched the x's and the y's. We did that for all these points to get some points. And now we're going to use it to find our asymptote. Give me at least one guess before we move on, even if it's a terrible guess. Even if your guess is like a watermelon or something. That's not even an answer. How could an asymptote be a watermelon? But at least give me something. The hint is that we are switching the x's and the y's for inverse functions. Yes, exactly. Very good. Very good, right? If the asymptote in the original function was y equals 0, for the inverse it's going to be x equals 0. That's this vertical line. This vertical line is our asymptote. So we have an asymptote here. Now we just connect the dots. It gets really, really close to the asymptote, then curves up like this, and goes in that direction. And again, we have that really nice similarity between a function and its inverse. Remember, inverses, switching x's and y's, always have this nice reflection quality. Oh no, not fake Gabe again. All right, so let's look at this again. Again, tying everything together, because you have an exam next. You have an exam next week. You have a final the week after that. So the more we can tie things together, the better you're going to be. Remember inverse functions, right? We said here was an inverse function, right? X cubed. The inverse function of x cubed was the cubed root of x, right? And we had that sort of symmetry thing going on here. They're sort of reflections, just switching all their x's and y's. Well, what we just did is we just graphed 2 to the x, an exponential function, and log base 2 of x, its inverse. And we have that same situation. See how they have that reflection? Okay. And then 2 to the x, the blue graph, has an asymptote on the x-axis. It gets really, really close, but it never touches. The logarithm has an asymptote on the y-axis. It gets really, really close, but never touches. It looks like it touches here, but it's not, right? Look, it doesn't say x is 0. X gets close to 0, but x never actually hits 0. All right, and as x gets bigger, y gets bigger. We move along like this. All right. So you have 2 ways of graphing in this section. Well, more than 2, but 2 big ways. If you want to plot the exponential function first, since these are usually easier to plot, and then just switch all the x's and the y's to get your logarithm, that works. Or you can make a table and plot your logarithm that way. All right. That's the main thing that we're going to do when we talk about this stuff. So, we have a ton of things to talk about for not that many things, but we look at the domain, we look at the range, we say, is this function 1 to 1? What's the asymptote? We already talked about this stuff, right? The domain. Oh, remember also things about inverse functions. Inverse functions, switching the x's and the y's. So the domain of blue is the range of yellow. Domain of an exponential function, we said, is always all real numbers. The domain is all real numbers. We can get any x we want here. That means the range of the orange is all real numbers. The range of the blue graph, we said, was 0 to infinity, which means the domain of the orange graph is 0 to infinity. And again, they both have to be 1 to 1, because otherwise they wouldn't have inverse functions, and they are inverses of each other. Okay, and we already talked about the asymptote as well. So we're going to use that as we go on. So, right. Reminder for talking about domain is you can't take the logarithm of a negative. Okay? Right? What is the logarithm of -2? Well, where does the graph hit -2? Right? There is no x coordinate at -2 here. Another way to see why we can't take the logarithm of a negative is let's try to take the logarithm of a negative, right? What is log base 2 of -4? Well, we learned yesterday we want to put this in exponential form. In exponential form, 2 to what power is going to give you a -4? And there's no answer to this. And again, another way to see that there is no power we can raise 2 to get a negative number. Another way to do that, or see how that works, is we can look at exponential functions. 2 raised to what power is going to give us a -2? Well, we never go down here. All right. So there's no answer. No answer. So that means this does not exist. All right. So with that in mind, with this in mind, we cannot take the logarithm of a negative number. Let's find the domain and range. Find the D and range. Yes, very consistent. Part A, f of x equals log base 2 of x plus 3. This is very similar to stuff we've done all the way back in Math 930. Remember the good old days when we met in Rock Springs main campus, room 1225? We'd come to class early. We'd chuckle, make some jokes, talk about rational expressions. Now we're in the dark days. You're sitting at a screen trying to learn some math. And I'm ready to throw my cats out of my room. No, that was 920. It was the pizza. Those were dark days too. Okay, so we can't take the logarithm of the negative number. We need the inside to not be negative. Well, we can't take the log of a negative or 0. So we need this to not be negative or 0. So we need it to be positive. Okay. So when is the inside positive? Whoa! Just like Math 930, right? Solve this inequality, give your answer in interval notation, just like 930, just like the beginning of the semester. Okay, so we just subtract 3 from both sides. Okay, this is true, and x is... that's not right. Hold up. I can solve inequalities. I'm very good at it. When x is greater than -3. Okay, so our domain is -3 to infinity. And just like in 6.2, which you have a quiz on today, just like in 6.2, when I said what is the domain of an exponential function, the domain of any exponential function is all real numbers, all the x values. Likewise, the domain of an exponential function is the range of its inverse, the range of literally every single logarithm problem. Range is the y values, is always going to be all real numbers. Okay? That's how you do this. There's another way to have found the domain and the range of this problem. Is you could look at your basic function and transformations. Right? You could have said, okay, what's our toolkit function here? Log base 2 of x has a domain of 0 to infinity and a range of all real numbers. So what's our transformation? Right? This is a transformation. It's just left 3. So our domain and range get moved left 3. Range is y value, so moving to the left doesn't affect the range. But moving the domain to the left makes it negative 3 to infinity. Okay? Any questions here before we do part B? All right, f of x is equal to log of 5 minus 2x. Wait a minute. Jason, you must have written down the problem wrong. Where's the base of the logarithm? What's the base of the logarithm here? I didn't write it down. Anyone remember? Someone remembers, right? Talked about it yesterday. Yeah, the base is 10. Good. This is the common log. Base 10. All right. The domain is negative 3 to infinity, Lexi. So if we move it left 3, then it becomes negative 3 to infinity. What I was trying to say here is that if we look at the basic function, that's 0 to infinity. But in part A, we're moving it left 3. So it becomes negative 3 to infinity. All right. Does that answer your question? Good, good, good. Great. So the transformation method is a little bit more confusing here because it's slightly more confusing transformations. But again, the idea is the same. We need to take the logarithm of a positive number. So we need the inside to be positive. So try to solve this. What's our domain going to be for part B? And while you're doing that, we can also do the attendance question today. And for the attendance question today, you will tell me whether you prefer light mode or dark mode. So this is like dark mode. This is light mode. A lot of websites have light mode or dark mode. There's no right answer. Anyone who tells you there's a right answer is a jerk. Okay? So there's no right answer, but do you prefer light mode or dark mode? And while you're taking the attendance question, find the domain. So what do? We solve for x. Let's subtract 5 from both sides. Let's divide both sides by negative 2. When we divide by a negative, the sign switches, and we get x is less than 5/2. So an interval notation that says the domain is -infinity up to 5/2. And the range is the easy one, right? The domain of an exponential function is always all real numbers, which means the range of a logarithmic function, its inverse, is always all real numbers. So every single one of these, the range, this is a freebie. Is that how you spell freebie? If you can even see it. Okay. Let's go on to part C. Part C is a good one. Oh, I wish I had part C on the same page as part B. Here. We're going to make it be on the same page. Part C. G of x. Find the domain and range of this function. And again, right, remember this is the natural log. Base E. So they just switch if it's inverse no matter what. The domain and the range of any function and its inverse, yeah. But the problem is, right, the inverse of this function is a little harder to see. Right? It has the inverse of this function has to do with 10 to the x, but there's some transformations here. So the inverse function will also have some transformations, so it's a little harder. But in general, yeah, logarithms and exponentials are inverses, so this is going to be r always. So you can give me the answer to part C without writing anything down. You can find the answer to part C without writing a single thing on your paper. Does anyone have it? Any guesses? Because that's the right idea. But it's not the opposite of part B, it's the same. So it's interesting that for logarithms, right, to find the domain, we only look at the inside, right? The range is always all real numbers. And for domain, you only look at the inside. Right? Which means that everything that's not on the inside doesn't affect the domain. So we already found it. It's just going to be the same as before, -infinity to 5/2. So it doesn't matter whether we have the common logarithm, natural logarithm, log base 2. Doesn't matter if there's a plus 22 on the outside. Okay, because the domain only looks at the inside. And the range is always all real numbers. Okay, so a little trick right there for anyone who likes doing things a little faster. Okay. Good. Let's maybe do the next 2 examples and then review for the quiz if we have time. Then we'll make good progress. Again, if we make good progress, like people are answering good questions and we're going through it fairly quickly, I do like to have Fridays be a little shorter than normal. We can have a nice, relaxing Friday. It looks like we're on track to do that. So keep answering questions and we should have a nice chill day tomorrow. All right, example 3. Graph on the same axes. Part A. Y equals log base 3 of, excuse you, Jason, log base 3 of x. So remember, I said there's 2 ways of graphing this. We could graph its inverse function, 3 to the x, then flip all the x's and y's, just like we did in example 1. Or we could make a table. Let's make a table. Okay? We have our graph. All right, and our table, it's just going to be some x's and some y's. Fun fact, by the way, if you really want to be clever, you can kind of do this backwards, right? Where the y's are the x's of the inverse function. But let's get some review, right? So what if we plug in x equals 0? We love x equals 0. X equals 0 is a great thing to plug in. So we say, okay, what's log base 3 of 0? I don't know. Logarithms, sometimes hard to work with. Let's put it in exponential form, right? Go off to the side somewhere. What's exponential form of this? 3 to what power equals 0? There's no answer to this. The range of 3 to the x is all positive numbers, not 0. And the domain, right? We said the domain, we can only plug in things bigger than 0. So if we're plugging in 0, this doesn't exist. Okay, so 0 wasn't a great choice here, because the log of 0 is not a real number. So let's plug in something else. And we have an asymptote at 0. Let's plug in 1. So when you say, okay, what is log base 3 of 1? 3 raised to what power is equal to 1? What exponent do we raise the number 3 to get a 1 on the outside? Somebody give me the answer. Close. 3 to the first power, oops, would actually equal 3. 3 to the 1/3 power is the cubed root of 3. 3 to the 0th power is 1. So this is equal to 0. So when x is 1, y is 0. We plot that point. Now we could try plugging in 2, but 2 is not going to be something good to plug in. This goes back to evaluating the logarithms from before. Do you remember properties of exponents that say any number raised to the 0th power equals 1? Because that's important. Okay. Fractional powers give radicals. 0 powers always make it 1. Negative powers give fractions. Let's do this a different way. Let's see if this a different way makes more sense to you. Okay. Watch this. Let's try something else. If you're good with logarithms, you can do it this way. But if you're still learning logarithms, like I imagine pretty much everyone is still learning logarithms right now. What if we just looked at the points on the inverse function? What's the inverse function here? 3 to the x. What we can do is can look at the inverse function. Right, the inverse function of log base 3 is 3 to the x. Inverse of a logarithm is the exponential. Right? We could just do this and then switch the x's and the y's like we did in example 1. So, if x is 0, 3 to the 0th power equals 1. When x is 1, 3 to the first power is 3. When x is 2, 3 squared equals 9. When x is negative 1, 3 to the negative first power is a third. Just plug in a whole bunch of points and see all these points that would be on the inverse function. And then to graph the logarithm, we just switch these x's and the y's. So again, for 3 to the x, the x is 0 and the y is 1. But we're graphing the inverse. So we're going to have x be 1 and y be 0. That's where this 1, 0 comes from. This makes more sense? Good. I'm glad you brought it up. Thank you, Lexi. This is the inverse function. When x is 1, y is 3. So flip it. X is 3, y is 1. Now flip these ones. X 9, 2. Is right here. What? I have a hole in my paper. Where did that come from? Oh. You don't actually want to know where the hole in my paper comes from. I was getting very into things. You don't want to know, but I'm going to tell you anyway. I was getting very into things, and so it just got wet. But that's that point, right? And then this last one, flip the points. When x is 1/3, y is going to be -1. So this is our logarithm. Like so. We're going to do part B, and then we're going to do a quick review before the quiz. Okay. So part B, remember, we're supposed to be graphing these on the same axes. So for part B, graph f of x equals log base 3 of x minus 2. So we're going to do this in red. And I'm going to say that part B is going to be a lot easier than part A. You could do the exact same things. Finding the inverse function here is a little trickier. Function transformations are going to be a lot simpler. So you have to find the inverse function, Lexi. So as soon as it gets a little bit more complicated, the inverse function is a little bit more complicated. But if you really like the inverse method, you could find the inverse function. Right? To find the inverse, we switch the x's and the y's and solve for y. And we haven't really talked about how to do this, but I think you could. I think you, Lexi Chenoweth, or whoever you may be with that username, can solve this, because we just put it into exponential form. The base of the logarithm is going to be the base of our exponential. And it becomes like this. So here the inverse function is 3 to the x plus 2. That's the inverse for part B. So if you like inverse functions, you can do that. And again, there's that relationship, right? This is a logarithm moved right to. Well, its inverse function is the exponential moved up to. So again, if you wanted to find the x's and y's of this function and just switch them to do the graph, go for it. Or you could use function transformations. Right? To say everything is right to. So multiple options for this section. All right. So what we're going to do for the class is just move every point on this graph right to, because we were supposed to do it on the same axes. All right, so if this point gets moved right to, it just becomes right there. This point goes right to, it comes right there. This point goes right to, this point goes right to. And what does our asymptote become for the red graph? For part B, our asymptote is just moving everything to the right 2 units. So what is our asymptote for part B? And then that'll pretty much finish up the set part of the section we're doing today. Very, very close, and that's the idea. I think you just said it wrong. It's x equals 2, but yeah. Good. So our red graph looks very similar. Just shift it over a little bit. All right, and that's how you do example 3. Because the asymptote here was x equals 0, so move that 2 over as well. And the asymptote becomes x equals 2. All right, all good guesses. I appreciate answering the question. Okay, so if there are any more questions about this problem, we can I can answer them. Or if you have questions in the quiz, we're going to review a bit for the quiz next, okay? So your quiz today is only going to be on 6.2. Okay. Oh, I had my other class up and I was like, chapter 10. No, that's not good. Oops, I didn't include it in the title, but it should be only on 6.2. Your next quiz will have more stuff on it. Okay, so today homework 6.2 is due. Quiz, it's on 6.2. And 6.2 was, oops, that's not right. 6.2 was graphs of exponential equations. So one of the big things for graphing things, remember, was just like remembering what exponential equations look like. Where this is our starting value, 3. And then this is our growth or decay rate. So it's a decay rate right here. You can just make a table for all this stuff. Okay. If you ever want to graph something, you can do it a shortcut or you can do it the long way. And the long way will always work. And that's just make a table of your x's and then plug that into your calculator. And again, just a big side note, be very careful. You cannot combine this 3 and this 1/4. They do not combine because the 1/4 has an exponent. Okay, so they have to stay separate. So you should be able to graph these things. I like problems like this, but I don't know about fitting like 8 functions on a single graph. You should know function transformations. You could be asked about function transformations on the quiz today. So, right, reflection about the x-axis is like putting a negative out in front. A negative on the inside is a reflection about the y-axis. Again, inside is horizontal stuff. So if you have like a plus on the inside, that's a horizontal shift. Plus on the outside is a vertical shift. If you have a negative on the inside, that's like a horizontal reflection about the y-axis. Negative on the outside is vertical, upside down, about the x-axis. We skipped the end behavior problems, so don't worry about those. Again, can you do function transformations? 4 units up means +4 at the end. 2 units to the left, that's a +2 on the inside. Remember, left is positive on the inside because things on the inside, horizontal stuff, for function transformations kind of work backwards from what you might expect. Okay. And can you find an equation with function transformations? Can you find the equation from a graph? Look at the asymptotes. The asymptotes will help you, right? So we know the asymptote here, the horizontal asymptote is at 1, y equals 1. This is the line that this exponential function never crosses. We also know it's upside down. So we know it's upside down. That means there's going to be a negative out in the front. Upside down, vertical, negative out in front. We know the asymptote is 1. So that means it must have got shifted up 1. So there should be a +1 in that function as well. This one, again, it's upside down, negative out in front. Got moved up 3 because this is where our asymptote is now. This one, again, got flipped upside down. This one also got flipped left to right. And again, this one also got moved up 3. This is where the asymptote is. Okay, so that's where you want to start with these ones. Try to identify some function transformations and then start trying to put things together, plugging in points to see whether you're right. For example, let's look at number 40, okay? Right? We said that it has a reflection in both directions. And we said up 3. Maybe you didn't see the both directions. What if you said, okay, what if you guessed 6.2, number 40? Right? What if you guessed that it was up 3 and flipped upside down? So a reflection about the x-axis. What you would have is y equals negative 2 to the x, right? These are all 2 to the x's. Yeah. And y equals negative 2 to the x plus 3. Let's say this was your guess. Let's say you didn't know that it got flipped horizontally. You plug in some points and check your answer, right? So what I mean by that is, right, if we plug in x equals 0, we get negative 2 to the 0th power plus 3. And you type that in a calculator. That's negative 1 plus 3 is 2. Okay. When x is 0, we got that y was 2. So is the point 0, 2 on this graph? No, it's not. Okay. So we know that this can't be the right function. So we missed some stuff. Okay. We also missed a horizontal reflection about the y-axis. Y equals negative 2 to the negative x plus 3. This is closer. You still have the same problem though, right? We plug in x equals 0. We get that y is 2. 0, 2 is not on the graph. Something else has to be missing. A horizontal shift. We missed a horizontal shift. Okay. So 0, 2 is not on the graph, but 1, 2 is. So maybe we got shifted to the right 1 unit. Okay. These are the hardest ones, which is why I'm trying to spend a lot of time on it. Right? 0, 2, not on the graph. But 1, 2 is. Maybe a horizontal shift right 1. Okay. So let's try negative 2, the negative x. And again, the way the order works, to move it to the right one, we're actually going to have to add a +1 right here. Even though this is normally left 1, it has to do because we already have this negative 1, this negative out here in front. Now let's see if this is our answer. Check 2 points. If you check 2 points, that'll always work. If x is 0, y is negative 2 to the first power plus 3. That should be 1. Is the point 0, 1 on this graph? I think there's one of these on the quiz, Lexi. And I don't think it's this problem. 0, 1's on the graph. Good. Let's check a second one to see if we got it right. If x is 1, what do we get? Negative 2 to the negative 1 plus 1 or 0 plus 3. When x is 1, we got that y is 2. Is the point 1, 2 on the graph? 0.1 comma 2 is on the graph. Good. Okay. This is like your worst case scenario for something like this. And that's how you approach them. All right. Just try to identify what you can easily see and then start checking some stuff. We wanted to put the 1 up here in the exponent because a horizontal shift means a shift on the inside. Okay. And the inside of an exponential function means the exponent. Okay. If we had the +1 on the outside at the end, that'd be a vertical shift. All right. Any other questions before the quiz today? I think we covered pretty much everything that's going to be on it. Okay, well then if there are no more questions, I will open up the quiz. Go ahead and get started. Good luck. See you tomorrow.